Bismillahirrahmanirrahim. Welcome everyone. Today we are going to start the topic which is very important in understanding the chemical bonding, and it is about the bond length. We have divided this topic under different headings, and the first heading is the some other names of the bond length. Bond length may also be called as the bond distance or internuclear distance or compromise distance. Bond length or bond distance. The third name is internuclear distance, which shows that it is the average distance between the nuclei of two covalently bonded atoms in a molecule. And why it is called as compromise distance? Because when two atoms are covalently bonded, there are certain forces of attraction and forces of repulsion between them, but they still remain bonded to each other. That is called as the compromise. And this distance at which they remain bonded, even having the forces of attraction and repulsion, that is called as the compromise distance. Now let's move towards the second heading, which is the definition of the bond length. Suppose that there are two atoms, A atom and B atom, and these are covalently bonded with each other. Then the average distance between their nuclei, this will be called as the bond length or compromise distance. So bond length is defined as the average distance between the nuclei of two bonded atoms in a molecule, and these bonded atoms are actually covalently bonded. So now let's move towards the third heading. A very important MCQ is asked from the third heading, that how bond length is measured. Do we use some physical techniques or we perform some chemical techniques in order to determine the bond length? Keep in mind that actually we use the physical techniques to find the bond length. And what are those physical techniques which are used? The physical techniques are electron diffraction, that may be the X-ray diffraction, or that might be the microwave spectroscopy. So these are three important physical techniques which can be used to find the bond length. Now let us move towards the example of the bond length. For example, the bond length between two carbon atoms which are bonded through a single bond is 154 picometer. So this 154 picometer is actually the average distance between the nuclei of two covalently bonded carbon atoms. Now next is a very important point, that bond length is a transferable property. What is meant by the transferable property? A transferable property is a property which remains same under different circumstances in the different molecules. For example, one of a very simple example to understand this is electronegativity. We know that electronegativity of fluorine is 4, and this electronegativity 4 is constant for fluorine whether we are discussing some organic compound or inorganic compound. So this is a transferable property which remains same under different circumstances whether we are discussing the organic molecule or the inorganic molecule. In the same way, bond length is also a transferable property. For example, when we are discussing the carbon-carbon single bond, its bond length is 154 picometer. And this 154 picometer is the bond length in both alkanes as well as diamond. You can see that the circumstances are different, the nature of the molecules is different, but the bond length is same. So this is a transferable property. Alkane are organic in nature while diamond is inorganic in nature. But in both cases the carbon-carbon single bond, that bond length is 154 picometer. So this same bond length shows that it does not depend upon the nature of the molecule. It remains same. It is a transferable quantity. Now next is it is additive in nature. What is meant by its additive in nature? Suppose that the bond is between a carbon atom and chlorine atom. You know that the atomic radius of carbon is 77 picometer and that of chlorine is 99 picometer. And when we find their bond length, which is actually the internuclear distance, so let me show that it is also the radius of the chlorine atom, that is 99 picometer. Whether you will show it in this direction or in this direction, it will be 99 picometer. So what should be the bond length between carbon and chlorine? That will be equal to 77 plus 99 mean 176 picometer. Additive in nature means that when we add the radii of the two bonded atoms, it becomes equal to their bond length. It is perfect when we are talking about the non-polar bonds. But if we are talking about the polar bonds, then the difference of electronegativity plays some role. But in most cases, if we are talking about the bond between two same atoms, then if we will add the radii of those same atoms, that will be equal to their bond length. So that's mean that bond length is additive in nature. Now let us move towards the next heading, and that is the dependence of the bond length. First of all, the bond length is inversely proportional to, or you may say it is directly proportional to, let us discuss firstly the simple parameter. Bond length is directly proportional to atomic size or atomic radius. So when the atomic size increases, the bond length also increases, and when the atomic size decreases, then the bond length also decreases. We know that when we move from top to bottom in a group in the periodic table, then atomic size increases. That's why the bond length also increases. For example, if we talk about the group 4A, Then carbon-carbon single bond is shorter, while the silicon-silicon single bond is longer. Why? Because the atomic size of the silicon is greater than atomic size of the carbon. But when we move from left to right in a period, we know that atomic size, due to greater effective nuclear charge, a stronger grip of the nucleus on the electron decreases. And as the atomic size decreases, the bond length also decreases. So, in the second period, the bond length of carbon-carbon single bond is greater than nitrogen-nitrogen single bond. Why? Because it is the element of group 4a and this one is from 5a. So carbon atoms are having greater atomic radius as compared to the nitrogen atom. That's why the carbon-carbon single bond length will be greater than the nitrogen-nitrogen single bond length. So this one is the first factor which affects the bond length, and that is the atomic size. Now the second, that is the difference of electronegativity. And bond length is inversely related to the difference of electronegativity. Means when the difference of electronegativity between the two bonded atoms will be high, then the bond length will be shorter. For example, we have silicon atom. The radius of the silicon atom is 117 picometer, while the radius of fluorine is 64 picometer. If we add these two radii, it will come out to be 181 picometer. So bond length, expected bond length, or the calculated bond length of the silicon fluorine bond, that should be 181 picometer. But when we look into the actual value of the bond length of the silicon fluorine bond, it is actually 154 to 159 picometer. Now you can see that the actual value of the bond length is lesser as compared to the calculated value. Why? Because when we calculate the value, then we consider it as a non-polar bond. The polarity is not in our consideration. But when actual value is calculated, it comes out to be for the polar bond. And you know, it is partial positive, it is partial negative. And there are some additional forces, electrostatic forces between two opposite poles, partial positive and partial negative. There will be attractive forces, additional attractive forces between these two opposite poles. And these additional attractive forces will make the bond shorter as compared to its calculated value. So this one was the second factor which affects the bond length. Now the third factor, that is bond order. Bond length is inversely related to bond order. Bond order means the number of bonds between two atoms. For example, if there is carbon-carbon triple bond, carbon-carbon double bond, and carbon-carbon single bond, it is having maximum bond order, and then the bond order is decreasing as we are moving towards the single bond. That's why the bond length will be shortest in case of the carbon-carbon triple bond, and it will be longest in case of the carbon-carbon single bond. Here it will be equal to almost 124 picometer or 1.24 angstrom. It will be equal to 1.34 angstrom or 134 picometer, and it will be equal to 1.54 angstrom or 154 picometer. So as the bond order is decreasing, the bond length is increasing, so they have inverse relation with each other. That's why when we talk about the alkynes, alkenes and alkanes, the bond length in alkynes is shortest then alkenes, and the bond length in alkanes is longest or highest. So this one is the order of the bond length in the alkynes, alkenes, and alkanes. Now let me tell you one thing, that in alkynes, when the triple bond is present between carbon atoms that are sp hybridized. In alkenes, when the double bond is present between two carbon atoms, they are sp2 hybridized. And in alkanes, there is sp3 hybridization. The S character in sp hybridization is 50%, in sp2 that is 33.3%, in sp3 that is 25%. So we can also conclude an other important point from here, that as the S character in the hybridization decreases, then the bond length increases. Why? Because greater the S character, S is a small orbital as compared to the P. So when there will be greater percentage of the smaller orbital, then obviously the bond length will be shorter, because the smaller orbital is contributing more in formation of that bond. So as the S character decreases, the bond length increases. So now we can also say that the bond length is inversely proportional to the S character. So we can also conclude that bond length is inversely proportional to S character. This one is another factor which is affecting the bond length. The next factor which affects the bond length is the bond energy. And keep one thing in your mind, that the stronger bonds are always the shorter bonds. Stronger bonds have high value of the bond energy, so they will be having low bond length. And when the bonds are weaker, means low bond energy, they will be longer, means their bond length will be quite high. So now let us talk about the last thing. Let's suppose that there is a bond between two carbon atoms. These are two carbon atoms, and you know that bond length will be 154 picometer. Listen very carefully. This is only valid when the bond is between two identical atoms. When the bond is between two identical atoms, if you divide the bond length with 2, that will become the covalent radius of that atom. So the bond length between two carbon atoms is 154 picometer. And if we divide the bond length with 2, then it comes out to be 77 picometer, which is called as the covalent radius of the carbon atoms. So here we can also define the covalent radius. That covalent radius is actually half of the internuclear distance between two identical covalently bonded atoms. So that will be. Now bond length is very important because it decides the bond energy, it decides the stability of the bond, and it also decides the stability of the molecules. This was a discussion about the bond length. I hope so it will be useful for you people. Next time we will come up with a new lecture. Take care. Allah Hafiz.